Hi, this lesson is about related rates. Related rates are word problems that calculate the rate of change of one quantity in terms of the rate of change of another. Both quantities change if there's more than one, sometimes there's more than two. One or more of those may be changing with respect to time, and therefore we're using concepts that we use in implicit differentiation in that topic. So when we solve these types of word problems, we want to identify the formula associated with the problem. Sometimes a picture might be helpful. Identify which parts of the formula are changing and which parts are constant. This is a really important step because anything that's changing will have a derivative associated with it, and anything that's constant will not. You want to make substitutions for the parts in the formula that are constant before you take the derivative. So anything that's constant, you have to substitute into the formula before you take the derivative. If necessary, make substitutions for variables in terms of another variable. That will happen in some instances where you have multiple variables and you don't have enough information about all of them, and there is some information that will allow you to replace one variable with another with information regarding another variable. Then take the derivative of both sides of the formula with respect to time. So you're going to be seeing dy dt's and dx dt's and dv dt's and a lot of things like that depending on your formula. And then solve for the related rate in question. And a related rate will be something that's changing with respect to time. And then remember to include your units. All right, so we start with some easy ones and then we work our way into some that are a little bit more difficult. So if V is the volume of a cube with an edge of length x, and the cube expands as time expands, find dv dt in terms of dx dt. So if you think of a cube, if an edge is expanding, is lengthening, then the cube will also, so as the side gets bigger, the whole cube does. So we need a formula, and since you're told that the length of an edge is x, your volume is x cubed. So when you take the derivative of both sides, the derivative of v as this cube expands over time is dv dt, and the derivative of x cubed, this is not with respect to x, this is with respect to time. So it's 3x squared times dx dt. So again, you can think of it as like chain rule, where the cubed is the outer function, and then you got to take the derivative of x. But the derivative of x is dx dt. So we've answered the question. dv dt is expressed in terms of dx dt. All right, so here's another one. Let's suppose that y is x cubed plus 2x, and dx dt has a value of 5. We want to find dy dt when x is equal to 2. So these two statements here indicate that both x and y are changing with respect to time. All right, so I have to take the derivative of both sides of this equation. So the derivative of y is dy dt. The derivative of x cubed is 3x squared dx dt. Derivative of 2x is 2 dx dt. Now we know what dx dt is. We know what x is. So we're ready to plug into the right side. And remember, we're solving for dy dt, which is on the left side. So you plug in 2 for x, 5 for dx dt, and you get a final answer that dy dt is equal to 70. All right, so let's get back to some geometry. So number 3 says each side of a square is increasing at a rate of 6 centimeters per second. At what rate is the area of the square increasing when the area of the square is 16 centimeters squared? All right, so I'm going to call the side of my square S, and so the formula I'm interested in is A is equal to S squared, because you know that we're talking about the area of a square. So sometimes you just have to read it in order to come up with where your formula is, and so and other times there's a picture. So we have a is s squared. Okay, so the derivative of both sides of this equation would be dA dt equals 2s times ds dt. Because as the side increases, the area will also increase. So my rate of change of the side is given to be 6 centimeters per second, and I'm asked to find the rate of change of the area because it says it's increasing, and increase is a change. All right, so in order to solve for dA dt, I need to know what s is, and I need to know what ds dt is. So again, you're told in the problem that the side is changing at 6 centimeters per second, but I don't know what s is, but I can use this information here. I want to find dA dt when the area is exactly 16 centimeters squared. So if a is 16, then, and remember a is s squared, take the square root of both sides, it means that the side is 4 centimeters. So now that I know that my side is 4 centimeters, I plug in 4 in for s and 6 in for ds dt, and multiply that out, and you get that dA dt is changing at 48 centimeters per second. So when the side is changing at 6 centimeters per second, at the moment of time when the area is 16 centimeters squared, the rate of change of the area is exactly 48 centimeters squared per second. And it's squared because it's a rate of change of area. Okay, here's another one. Air is being pumped into a spherical balloon, so its volume increases at a rate of 100 centimeters cubed per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Okay, so we're talking about a sphere. And the formula for sphere is 4/3 pi r cubed. All right, so as the volume increases, so does the radius. And as the radius increases, so does the volume. So there is no constant here other than these coefficients. So I know that when I take the derivative, I'll have a dv dt on the left and a dr dt on the right. Okay, so I did that here, took the derivative. So you have to use power rule on r cubed. So that's why you have 4/3 times 3 pi r squared. So the 3's will cancel here and here. So it's you end up with 4 pi r squared dr dt. Because remember, when you took the derivative of r, you got to follow it by dr dt. Okay, so in order to solve this, we have to figure out what do we know and what are we trying to figure out. You're told that the volume increases at 100 centimeters cubed per second. That's given here. That is your dv dt. So because the unit of measure gives it away, it says the volume increases. That means it's a rate of change for volume. And you want to find how fast the radius increases. So I want to find dr dt. When dv dt is 100 and you're told that the diameter is 50 centimeters. But notice that in my formula, I don't have a diameter, I have a radius. So if the diameter is 50, my radius is half of that, which is 25. So everything I need in order to solve for dr dt is here at the top. So I'm going to plug in everything I know. dv dt is 100 equals 4 pi, and then my radius is 25, so it's 25 squared times dr dt. Don't forget, that's what we're solving for, dr dt. So I'm going to divide both sides by 4 pi 25 squared. And then I took a little shortcut here. I canceled this 25, one of them, into the 100, and that's why I end up with, no, I did it actually the other way. I divided 4 into 100, which is why I have 25 over pi 25 squared, and then I also canceled this 25 with one of these. So your dr dt is 1 over 25 pi centimeters per second. That's an exact answer. If you were asked to round, you need a calculator and you would round appropriately, but only round if you're told to round. All right, so here's number 5. A ladder that's 10 feet long rests against the vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? All right, so you need a picture, and so here's my picture. We have a ladder leaning against the wall. So I'm going to let the distance away from the wall, to the ladder be my x, and the distance up the wall be my y. So I have created a right triangle with this picture. So the formula that I'm going to be using is x squared plus y squared equals, and remember you're told that the ladder is 10 feet long, so it equals 10, so this equation equals 10 squared, the hypotenuse squared. Now we're able to plug in 10 here right away. That's an example of a constant. So even if the ladder starts sliding, the ladder is still going to be 10 feet long. So the x and the y will change as this ladder slides away, but the 10 will be constant. All right, so that means I have to take the derivative of both sides of this equation here. And remember, both x and y are changing as the ladder slides. So I have 2x times dx dt plus derivative here would be 2y times dy dt. And the derivative of a constant is just 0. Okay, so what are we solving for? We want to know how fast the ladder is sliding down. So we want to find dy dt when the rate of change as it slides away is 1 foot per second. So when dx dt is 1 foot per second, and you're also told that you're trying to figure out what dy dt when the ladder is exactly 6 feet away from the wall. Well, that's going to be an x value. So for me to find dy dt here, I'm going to need to know what x is, and I do. I'm going to need to know what dx dt is, and I do. But I do need to know what y is. This is an unknown right now. So I'm going to use what I know in order to solve for y. So again, using the Pythagorean Theorem, when x is 6 and my ladder, my hypotenuse is 10, I can solve for y by just doing 6 squared plus y squared equals 10 squared. Subtract 36 from both sides, you get y squared equals 64. So remember, this is distance, so you don't want plus or minus 8. The answer is just 8. You can't have negative feet up a wall. So now I know my y value. So now I plug in everything I know so that I can solve for dy dt. So I have 2 times 6 times 1 plus 2 times 8 dy dt. This gives me 12 plus 16 dy dt. Subtract 12 from both sides, and then divide by 16. And when you simplify negative 12/16, you get negative 3 over 4. So the ladder is sliding down at negative 3/4 feet per second. And the reason it's negative is because the ladder slides downward, goes in that direction. If it was getting pushed horizontally and the ladder would be sliding up, then you would get a positive answer. Okay, here's another one. This one says a cylindrical tank with a radius of 5 meters is being filled with water at a rate of 3 meters cubed per minute. How fast is the height of the water rising? And so here's the formula for a cylindrical tank. So remember, they look something like this. So water is getting poured into this tank, and so the height of the water is rising. So as the water goes in, the height changes as well as the volume of the amount of water in the tank, but the radius of the tank is a constant. So that's something important to keep in mind, because with constants you need to replace them. And you're told that it's got a radius of 5. So we know that this 5 is not going to change no matter how much water is filled in there. All right, so how fast is the height rising? So you want to find dH dt when your dV dt is 3 meters cubed per minute and your radius is 5. Okay, so here's my formula. V is pi r squared h. Remember I told you at the beginning of this lesson, if you have a constant, replace it before you take the derivative. So radius is 5, that will not change. So your formula that you need to take the derivative of is 25 pi h. Well, now I'm ready to take the derivative. Both volume and height will change as water fills. So I have dV dt equals 25 pi dH dt. Then we know that dV dt is 3. We know we're solving for dH dt. So all you need to do is divide both sides by 25 pi, and you get that dH dt is 3 over 25 pi meters per minute. And again, that's an exact answer. Don't round unless you're told to round. Okay, here's another one. Whoops. So here's another one. Gravel is being dumped from a conveyor belt at a rate of 30 feet cubed per minute, and the coarseness is such that it forms a pile in the shape of a cone, whose base diameter and height are always equal. How fast is the height of the pile increasing when the pile is 10 feet high? And the formula for a cone is 1/3 pi r squared h. So it's similar to the formula for a cylindrical tank, except this one has a third in front. So imagine here's my pile of gravel, and as the gravel falls into this pile, I have a radius here and a height that's changing because the pile just keeps getting wider and higher. You're told that the volume is changing at 30 feet cubed per minute. And you know that you want to know how fast the height is increasing. So I want to find dH dt. But when I look at my formula, here I have 1/3 pi r squared h. I don't really know anything about r other than the height and of the pile and the diameter are always equal. But I don't know what dr dt is, so I really need to get rid of that variable. So I'm going to use the information that I was told. I was told that the diameter equals the height. Remember, the diameter is twice the radius. So that means that the radius is equal to the height divided by 2. So using that information, because I do know something about my height is 10, that's given, I'm going to replace the r with h over 2. So from this line to that line, that's exactly what I did. There are no constants in this formula. Radius and height and volume are all changing, but I don't know much about radius, so I need to get rid of it. And so that's what we're doing, replacing that in here. All right, so when you simplify this, you get that the volume is 1/12 pi h cubed, which is good news because now I just have to deal with volume and height. And I'm ready to take the derivative. So the derivative of volume is dV dt. The derivative of 1/12 pi h cubed, you're just doing power rule. So it's 3/12 pi h squared followed by dH dt. And then I simplified the 3/12 to give me 1/4, but I also replaced what I know. I know that the volume is changing at 30 feet cubed per minute, so that goes on the left. I know that my height is 10, so I plug that in on the right. And then I have to solve for dH dt. So here you're left with 30 equals 1/4 pi times 100. The 1/4 and 100 simplifies down to 25 pi dH dt. Then divide both sides by 25 pi, and you get dH dt is 30 over 25 pi. But 30 and 25 have a common factor of 5, so you get dH dt is changing at 6 over 5 pi feet per minute. All right, let's move on to another one. This one's about a plane. So a plane flying horizontally at an altitude of 1 mile and a speed of 500 miles per hour passes directly over a radar station. Find the rate that the distance from the plane to the radar station is increasing when it is 2 miles away from the station. All right, so here's my radar station. The plane flies above it and is moving away in this direction. You're told that the altitude is 1 mile, so that's not changing. But the x and the z are changing. So x is the plane's direction, and we know that the plane is moving at 500 miles per hour. So that means that, again, anything that's something per unit of time will be a derivative. So dx dt is 500 miles per hour. And you know that you have to find how quickly the distance from the plane to the radar station is changing. So that means I need to find dz dt when z is equal to 2 and dx dt is 500 miles per hour. So similar to when I did earlier, this again creates a right triangle. So I'm able to use the Pythagorean Theorem, but different information is presented. You know, the one leg is 1, the other one is x, and you don't know that you can't plug in the hypotenuse. You can't plug in 2 because that is changing. You're going to use the 2 later on. So the only thing that's constant is the height. So you have x squared plus 1 squared equals z squared. Take the derivative on both sides with respect to time. You get 2x dx dt plus 0, because the derivative of a constant is 0, equals dz dt. And now I know that I have to solve for dz dt. I know what z is. I know what dx dt is, but I don't know what x is. So again, I need to go back to the Pythagorean theorem right here and figure out what x is when my z value is 2 and the height here is 1. So x squared plus 1 squared equals 2 squared. That means x squared equals 3. And so you get an x value of root 3. So now I can plug in everything I know in order to solve for dz dt. So I have 2 root 3 times 500 equals 2 times 2 dz dt. All right, so 2 times 500 gives me 1,000 root 3, and then divide by the 4 that's on the right side. So I get 1,000 root 3 over 4, but 4 goes into 1,000 250 times, so you get that dz dt is changing at 250 root 3 miles per hour. So that's how quickly the rate of change is between the radar station and the plane when it's exactly 2 miles away from the radar station. Okay, so here's another one. This is number 9. So it says, a water tank has the shape of an inverted circular cone with a base radius of 2 meters and a height of 4 meters. If water is being pumped into the tank at a rate of 2 meters cubed per minute, find the rate at which the water level is rising when the water is 3 meters deep. And again, it's a cone, so we're going to use the same formula again, 1/3 pi r squared h. All right, so I'm here, and again, I don't really know anything about dr dt or r, But I do know that you need to find dh dt, so we definitely don't want to get rid of h. You're told that h is 3 meters at some point, but you're also told that there's some relationship here, that the base diameter is 2 when the height is 4. So that means I can set up a ratio of like similar triangles. So r is to h as 2 is to 4. And what that will allow me to do is solve for r. So you get r is equal to 1/2 h. So you simplify the 2 over 4 and multiply by h. R is equal to 1/2 h. So that value gets plugged into your volume formula, again, so that we are only dealing with volume and height, not this r variable that I don't really know anything about. Okay, so I square that and I combine the h's, and the 1/3 and 1/4 becomes pi over 12 h to the 3rd power. Now I'm ready to take the derivative of both sides. So I get dv dt equals, and then use power rule, it's 3 times pi over 12 h squared dh dt. The 3 pi over 12 simplifies down to pi over 4, but I can also replace what I know. You were told in the original problem that dv dt is 2, and that when you're trying to figure out dh dt, the height is 3. So you get 2 equals 9 pi over 4 dh dt. But dh dt, you need to solve for it, so multiply both sides by the reciprocal of this, and so you get dh dt is equal to 8 over 9 pi, and the units here are meters per minute. Okay, this is the last one. This one allows us to use a little bit of trigonometry. So it says a hot air balloon rises vertically, is tracked by an observer located 8 kilometers from the liftoff point. At a certain moment, the angle between the observer's line of sight and the horizontal is pi over 4 radians, and it is changing at 0.7 radians per hour. How fast is the balloon rising at this moment? All right, so I've drawn a picture. Here's my hot air balloon. Here's my observer looking up at the hot air balloon. Here's the angle that was referred to. This is the angle of elevation. And so you want to find out how fast is the balloon rising. So you need variables here in order to make up an equation. So I'm going to let this vertical side be h. The observer is exactly 8 kilometers away, so that's a constant. And I really don't know anything about this side, but I don't really need it because I can use my tangent function in order to solve this problem. Tangent function uses the side opposite and the adjacent side, so I don't need the hypotenuse at all. So your equation that you're going to take the derivative of is tangent of theta equals h over 8, which we know means 1/8 h. So I have to take the derivative of both sides because both the angle and the height are changing as the balloon rises. So the person's line of sight will keep, the angle will keep getting bigger. So I have tangent of theta equals 1/8 theta. The derivative is secant squared of theta equals secant squared of theta times d theta dt equals 1/8 dh dt. All right, so I know a lot of this information. I need to solve for dh dt, so I multiplied both sides by 8 to get rid of that 1/8, and then I started plugging in what I know. You're told that the angle is pi over 4. You're told that the angle is changing at 0.7 radians per hour, so that's 0.7 is d theta dt. So pi over 4 is an angle that you should know without using a calculator, so it's the reciprocal of cosine, so that's 2 over root 2 squared. times 0.7. And when you simplify these two, 8 times 2 over root 2 squared, you'll get 16 times 0.7, and 16 times 0.7 gives you 11.2 kilometers per hour. All right, so that's it for this lesson. Give the homework a try. Good luck.